All right, welcome back, ladies and gentlemen, from break. This is your first video lesson back from break. I hope you all had great break that was restful, and that you all had something to take away from break that was hopefully something peaceful, and hopefully you're away from a screen. We are going to go through lessons 5.1 and 5.2 today, talking about linear functions, okay? In the beginning, we're going to talk about linear functions, what they are, how to recognize them, and how to graph them. And then on 5.2, we're going to learn a shortcut to graphing that is going to be very important. So without any further ado, let's get rolling. All right, so first thing we have here is a word problem that I think is pretty easy for us to tackle. A race car can travel up to 215 miles per hour. If the car could travel continuously at this speed, meaning it doesn't vary, it always goes 250 miles per hour, the equation y is equal to 215x gives us the number of miles y that the car drives after x hours. So in x hours, right, if it's 5 hours, we can substitute 5 in for x. It'll tell us how many miles it's traveled. Solutions are drawn in the graph below. Our first question is whether or not this is a function. And that goes back to our last module. And we can look at the graph here and see like, well, clearly this passes the vertical line test, right? It doesn't hit two places and when we draw any lines. So yes, this is a function. And it's asking us to complete the table below. And this is pretty simple because all we're doing is picking out, I'm going to clear my ink here. All we're doing is picking out corresponding points, right? So my x value here for my first hour is 215 miles. For my second hour, I have 430 hours. After 3 hours, I have 645 miles. For 4 hours, it's 860. And for 5 hours, it would be 1,075 miles. Fun fact. I just learned about this thing called Cannonball Run, which is like an underground racing thing from New York to LA. And my brother-in-law was telling me about this, and the world record holder for that did it with an average speed of like 110 miles per hour going from New York to LA. Cannonball Run, it's a crazy thing. Don't do it, but maybe look it up. Anyhow, all right. So more math stuff. Okay, the graph of a non-vertical, which means it's slanted, right, has a slant. Non-vertical straight line is called a linear function. So a straight line here, linear has the word line in it. So if you hear linear, think straight line, okay? It says, what are some examples that we have done in class that would not be considered linear? Well, there's lots of different examples we've had, but our general idea is that it's any function with an exponent that is other than 1. So if we've seen any function that looked like y is equal to x squared, that would be not a function. Do you think this would be a function? I'm sorry, do you think this function would be linear or not? Y is equal to x to the third. Well, we just said if the exponent is anything other than 1, which this is not a function. So we would say no right away. And that would be a reason why. And we could fill out this table and say, all right, 1 to the third power is still 1. 2 times 2 times 2 is 8. 3 to the third power is 27. 4 to the third power is 64. And I think 5 to the fifth power is 125. We can see that there is no common difference here, right? And if there's no common difference, then it's not linear. And if we think about what this graph might look like, we can also see further that it is not a straight line because, say, 1, 1 might be here, then 2, 8 would be here, and then 327 would be a lot higher than that. And we explode really quickly here. So we'd have a really steep line that looks like this, okay? For those reasons, it's very clear that it's not linear. It really goes back to this idea that it has an exponent. Okay. So what else can we learn about linear functions and what makes them linear? So a linear equation is linear if it can be written in what we call standard form. And standard form looks like ax plus by equals c. So the basic idea is that x and y are written on the same side, and they're set equal to a remaining number, okay? A and B and C are real numbers, and A and B are both not zero. And just think about that for a second. If both A and B were 0 here, we would have 0 equals c, which makes no sense, right? So that's just kind of like a weird rule about it. Here's what I want you to dial in on, okay? These are like the disqualifiers for what is not a function. If ever you see any of these things, right away, you're going to say to yourself, this is not a function, because questions are going to be like, is this a function? And you're going to look for these things. So x and y, so it says, notice that when a linear function is written in standard form, it has these things. So x and y both have an exponent of 1. So if there are exponents not of 1, it's not a function. It says x and y are not multiplied together. So if I see something like x times y equals 4, that is not a function. Okay, so I guess I can write an example for this one. If I see like x squared, I wrote a 2. If I see something like x squared plus y equals 6, not a function because of the square, right? X and y do not appear in denominators. So that means I can't have like 2 over x plus y equals 6. That's not a function. I'm sorry, not linear. And they do not, and the exponents, they don't appear in exponents and they don't appear in radical signs. So the exponent part means I don't have 2 to the x plus y equals 6. That would not be a function. And radical signs would be like, a radical sign is like the square root sign, right? So if I have the square root of x plus y equals 6, I know I've used the same kind of example here, but this would not be a function, right? So here's the things we look for, okay? If you ever see a squared value, not linear. If I ever see x and y multiplied together, not linear. If I ever see x or y in a denominator, not linear. If I ever see x or y in an exponent, not linear. And if x or y is in a radical sign, not linear. All of that means not straight lines. So let's test that out. Are the following equations linear or not? How do you know? If so, identify the a, b, and c values. Now, the a, b, and c values here, I'm going back to this thing, are the coefficients on x and y and standalone number, okay? That's what the a, b, and c values are. So I'm going to just rewrite this, ax plus by equals c. So does this have any of those disqualifiers? Number 2, does that example have any disqualifiers? And I would say no, it doesn't have radicals where x and y are in it. It doesn't have x or y in an exponent. All of those things work. So it does look like this, which means this is a linear function. This would be a graph of a straight line. And my a value is equal to 7. My b value is actually equal to -4. And my c value equals 12. Number 3, is this linear or not? Well, because x is in the denominator, it would not be a straight line. So this would be no. And in a problem like this, all you have to do, like in order to like say how you know, just circle the thing that makes it not linear. Okay. This one is almost in standard form. Remember, standard form has x and y on the same side. So we can make it that. All we have to do is subtract 5x to the other side. So now -5x plus -3y is equal to 16. And now this is in standard form. And I can say that a is equal to -5, b is equal to -3, and c equals 16. And because it's in standard form, I can say that this is a linear function. This right here has a radical with y in the radical, the square root of y, which means that this would be no, this would not be a straight line. This is not linear. These would not be straight lines. So both of these work, right? Both of these work. Neither of these do, okay? And remember, it goes back to these disqualifiers we talked about before. If you ever notice any of these things, right away, not linear, not a straight line. Okay, so that's going to be our main thing. We're going to be asking you if the equation given to you is linear, is it going to be a straight line? And if so, can you graph it? So let's go into that pattern. So first one here. Is it linear? Well, it's linear if we can put it in standard form. This is not in standard form, but I don't notice any square roots. I don't notice any exponents or fractions where the variable is in the denominator. So all we have to do is put this one in standard form. So to do that, I have to first distribute a 2. Okay? When I do that, I end up with negative 2x plus 12. And it's still not in standard form. I got to get my x to the other side. So I'm going to add 2x to both sides. When I get that, I have 2x plus 2y equals 12. Now it's in standard form. And now I can say, yes, this is linear. And it said if it's linear, then go ahead and graph it. So what I then have to do, every single point, I have to take my x values and substitute them in for x into the equation, and then find my corresponding y. Once I have a coordinate point, then I graph it. So here's what it looks like. My first value for x is negative 2. So negative 2 is going in for x right there. Times negative 2 is negative 4. I'm going to have to add that 4 to the other side to get 16. I have 2y equals 16. I would divide by 2 to give me that y equals 8. So that's my first value. So I have negative 2, negative 8. I'm going to know how to graph that. Negative 2, negative 1, 2, 3, 4, 5, 6, 7, 8. And this is my first point down here. Okay, and then I substitute in negative 1. 2 times negative 1 is negative 2. I add 2 to the other side to get 14. That leaves me with 2y equals 14. I divide both sides by 2 to get y is equal to 7. And so negative 1 and 7 is my next coordinate point. So negative 1, 7 would be right here. Then I substitute in 0. This one's easier. 2 times 0 is 0. That leaves me with 2y equals 12. I divide both sides by 2 to get y equals 6. So I have the coordinate point 0, 6. Right here. And I don't think I need to talk you through the rest of them. You can pause the video to take a look. I end up with the coordinate points 1, 5, and 4, 2. Or 2, 4 rather. So I'll graph those. 1, 5, and 2, 4. And there's my line. There's my graph of points. Okay. And notice this forms a straight line. So this would be my graph here of that line. And lo and behold, it's a linear equation, just like we said, because the equation was a linear equation. All right, next example. So is this a linear equation? If so, make a table and graph. So the same kind of thing. This one is already in standard form. I can tell you that my A value is negative 2, my B value is 1, and my C value is negative 1. And now I'm doing the same thing. So I'm going to kind of go a little bit faster through this. So I'm substituting in negative 4 in for x. 2 times negative 4 is negative 2 times negative 4 is positive 8. Then I have to subtract 8 to the other side. Negative 1 minus 8 is negative 9. So I get the coordinate point negative 4, 9, negative 9. So negative 1, 2, 3, 4, negative 9. I have to scroll down a little bit. It's going to be right here. Then I do the same thing for negative 2. Like that. Negative 2 times negative 2 is 4. I subtract 4 to the other side. Negative 1 minus 4 is negative 5. So I end up with negative 5 here. So I have negative 2, negative 1, 2, 3, 4, 5. And again, I'm going to go a little bit faster through here showing you what these are. You can pause the video and write them in. For 0, I get negative 1. For 2, I get 3. And for 4, I get 7. So I got negative 1, 3. I'm sorry, negative 1. I'm sorry, I said that wrong. For 0, I have negative 1. For 2, I have 3. 1, 2, 1, 2, 3. When I substitute in 4, I get 7. I move that point over. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And again, if we look at this one, it looks like I also get a straight line too. I will graph that. Oh boy, I wanted the line. Line. Boom. Looks something like that. Okay, so that's our basic question here. Give you an equation. We ask you if it's linear. You say yes or no based on whether or not you can put it in standard form. If you can put it in standard form, it is linear. Then once you understand it's linear, you can substitute x and y values, x values in, find y values, and then you graph those points. That's our process so far. All right. I have a problem set up here. This is going to be a word problem about Christoph selling umbrellas. So Christoph rents a kiosk in the mall to open up an umbrella stand. He pays $6 to the mall owner for each umbrella that he sells. The amount Christoph pays is given by the function f of x is equal to 6x, where x is the number of umbrellas that are sold. Graph the function, give its domain and range. So I got this all set up for us. And I think it's pretty clear to see that our domain values for x, umbrellas that we're going to sell, the numbers that make sense are 0, 1, 2, 3, and 4, because I can't sell a half an umbrella. Selling negative umbrellas doesn't make sense. So that's my domain. And I can sell potentially an unlimited amount of umbrellas. So that's why we have our dot, dot, dot here. And that's what I have set up in our graph. Our range is then directly related to that domain. So in this function, and I'm just going to, because that's not what I want to do. Undo that. Jeez. Because this is pretty good mental math, I'm not going to write out all the stuff for substituting, right? So I'm going to just keep it as it is. And let me get back my small marker. And I'm just going to substitute one at a time, right? So if I substitute in 0 for x, well, obviously I make $0. So my y value is 0. So I have the point 0, 0 on my graph. If I sell one umbrella, I make $6, or I'm sorry, I have to pay $6 to the mall owner. So I got 1, 6. I should have maybe marked this. I'll do this. 2, 4, 6, 8. If I sell 2 umbrellas, that means that I owe $12. So 2 times 6 is 12. So 212. If I sell 3 umbrellas, 3 times 6 is 18. So I got 318. If I sell 4 umbrellas, 6 times 4 is 24. And I can keep going, but I'm going to stop there because we get the idea. And this would be a discrete function, by the way, so I will not connect this. And my graph will keep going up by $6 every time I sell an umbrella. And then notice I have this marked off by 6, so my next one would be here, my next one would be here, my next one would be there. And that's what my graph looks like. And it's a straight line, it's linear. And we know that because all of this passes those disqualifiers, right? I don't have any square roots. I don't have x or y in the denominator. X or y is not an exponent. X and y are not multiplied together. All that good stuff. Okay, so right now, at this point, if I give you a function, say 2x plus 4y equals 16, you should be able to make a table, substitute in x values, come up with y values, and then graph it, okay? One thing you're probably noticing is like, that takes kind of a lot of work, okay? So in 5.2, we are gonna learn about using this intercepts method. Now the intercepts method helps us graphing because we only have to graph 2 points. Think about it. If I have a point here and I want to make a line, all I need is one other point to go through in order to draw a line. So we're going to find 2 points in order to draw a line. And we're going to do that by doing this method called finding the intercepts. So let's rock it. All right, first example, example 9. The miners are exploring 90 feet underground. The miners ascend in an elevator at a constant rate over a period of 3 minutes until they reach the surface. In the coordinate grid, the horizontal axis represents the time in minutes from when the miners start ascending, and the vertical axis represents the miner's elevation relative to the surface in feet. So complete the graph. It says what point represents the miner's elevation at the beginning of the ascent. So again, let's look at this graph here. So we got time in minutes on the x-axis, and we have the elevation below the surface, right? So like this point right here represents 0 time has gone by, right? And they're 100 feet below the surface. This point, for instance, right here would be like 5 minutes have gone by, and they are at 0 feet under they're at the surface, right? So it says they are initially 90 feet underground. Well, 90 feet underground before they start moving would be the point 0 for x and negative 90 for y. I'm going to put parentheses around it just to kind of emphasize that even though it's here. So I have the point 0, negative 90. That is 1 point on that graph. Now, all I ever need is another point on a graph in order to make a line. So let's look at the next one. It says, what point represents the miner's elevation at the end of their ascent? Well, it says that 3 minutes was the time it took for them to get at ground level. So that means at 3 minutes, they're at that ground level. So that's 3 comma 0. Again, I'm going to emphasize the coordinate point where we put parentheses and a comma in between. So I have 2 points, right? And this is a continuous function, so we can certainly graph a line here. So this would be the line that we graph. And I got that line there with only 2 points. By the way, this is the intercepts method because I used an x-intercept right here, and I used a y-intercept right there, okay? The x and y intercepts are where the line intercepts or crosses the x or y axis. And if we can find those 2 points, we can graph a line, and good thing, those are the 2 easiest points to find on a graph. So let's dig deeper into this. So, like I was saying, the y-intercept of the graph is the y-coordinate of the point where the graph intersects the y-axis. The x-coordinate point is always 0. What that means is that a y-intercept, I always abbreviate y equal like y-int for y-intercept, is always going to have the coordinate point 0 comma some number, right? Because you think about it, if this is the x-axis, that's the y-axis, the y-intercept is always going to be along this line. And what's the x value? Well, it's always going to be 0. Then for the next one, it says the x-intercept of a graph is the x-coordinate of a point where the graph intersects the x-axis. The coordinate of this point is always 0, of the y-coordinate is always 0. So what that means for an x-intercept, we always have a number and then comma 0, because y is always 0. And again, think of this. If we're finding an x-intercept now, right? That means I can't go up or down. I'm always along the x-axis, so my y value is always 0. Let's look at a graph, kind of observe what are the x and y intercepts. Well, again, a y-intercept is where it crosses the y-axis, and that's going to be right here. And that coordinate point right there is 0 comma 2 4 6. So 0 comma 6. Notice it follows the format, right? 0 comma some number. The x-intercept is here along this x-axis, and it's right there. So I have the point 2 4 comma 0. 4 comma 0. Okay. So that is how I identify an x and y axis. Notice if I were to graph this, I could just plot those 2 points and then draw the line. Now, we're going to use the intercepts method. Use the intercepts method to graph the following equations. And here's how we're going to do it. We're going to write the equation in standard form first. That is the easiest way to go about doing this. Put myself over here. Then we're going to find the y-intercept by doing the following. Because for a y-intercept, it follows the format 0 comma some number, right? Where my x value is 0, we're going to force x to be 0. So we're going to substitute 0 in for y. And then we're going to do the same thing for the x-intercept, where it is some number comma 0, and we're going to force y to be 0. So here's what it looks like. I have this equation, and it is not in standard form right now. So I have to subtract 2x from both sides in order to get it in standard form. So I'll have negative 2x plus 3y is equal to 18. Now it's in standard form. I know it's linear. Boom, we can go. Now here's what we do. For the x-intercept, it says simply to substitute 0 in for y. So 0 is going to go in for y. So negative 2x plus 3 times 0 is equal to 18. Well, that is then gone, right? 3 times 0 is 0. So I'm left with negative 2x is equal to 18. I divide by negative 2. And I get the coordinate point that x is equal to negative 9. Now, that is not the x-intercept. An x-intercept is a coordinate point. So I have to write it as negative 9 comma 0. So negative 9, 0 is right there. When I find the y-intercept, I have to substitute 0 in for x. So that's exactly what I'll do. 0 will now go in for x. So it's negative 2 times that 0 plus 3y is equal to 18. Negative 2 times 0 is 0, so that's gone. So I'm left with 3y is equal to 18. I divide by 3, and I get y is equal to 6. Now again, make a little squiggly here to separate. That is not a y-intercept because it has to be a coordinate point. So the y-intercept is 0, 6. So now 0, 6, 1, 2, 3, 4, 5, 6 is right here. And my line will look like this. That is not what it will look like. I thought I'd have a line graph there. I thought it chose the line tool. Something like that. Okay, let's pick a different color here. Let's do the next one. So I have another equation. All right, so 3y minus 5x, I'm sorry, 3y equals negative 5x minus 30. So again, I have to write this one in standard form. So I'm going to add 5x to both sides. So I will have, 5x plus 3y is equal to negative 30. So again, find an x-intercept. What do? I substitute 0 in for the other. Think about it this way. If you're finding an intercept, you substitute 0 into the other value of what you're trying to find. So if I'm finding an x-intercept, 0 goes in for y. So I'll leave you with 5x plus 3 times 0 equals negative 30. 3 times 0 is gone, so that leaves me with 5x is equal to negative 30. I divide both sides by 5, and I get x equals negative 6. So again, that is not my y-intercept, or I'm sorry, my x-intercept. It's a coordinate point, so I have the point negative 6, 0. I'll graph that in a second. Let's go ahead and find our y-intercept. So the y-intercept, I'm substituting in 0 for x. Do a little separation. So I'll have 5 times that 0 plus 3y is equal to negative 30. 5 times 0 goes away. So I'm left with 3y is equal to negative 30. Divide by 3 on both sides, and I end up with y is equal to negative 10. So again, that's not a coordinate point, so I need to have 0, negative 10. Again, where does that 0 come from? That 0 is what we substituted in for x in the first place. That 0 here is what we substituted in for y in the first place. Or I'm sorry, for x here, for y here. So I'm going to go ahead and graph those points. Negative 6, 0, 1, 2, 3, 4, 5, 6. And then 0, negative 10. 0, negative 10 is going to be down here. I know that. So now my line looks like this. I'm just going to sketch this one. It's not bad. So there you have it. That's how you use the intercepts method for graphing equations. Okay. A couple more examples here, word problems, and I have these ones kind of set up so they'll go a little bit faster. So let's dig into it. So a lake was stocked with 350 trout. Each year, the population decreases by 14. Bummer. The population of trout in the lake after X years is represented by the function f of x is equal to 350 minus 14x. And then interpret the intercepts of the function. So first thing we got to do, that's not what I want to do. Delete this. Is find our x-intercept, which means, again, we're going to substitute 0 in for y. So in doing so, 0 goes in for the f of x value now. It's not written in standard form this time. F of x, remember, means y, so I'm just substituting zeros straight up. So I now have to solve for x. So I have to subtract 350 from both sides. I'll have negative 350 on the left, negative 14 on the right. I'll divide both sides by negative 14. And when I do that, I end up getting x is 25, which is not the intercept again. Remember, I have to write it as a coordinate point. So we get 25, 0. Then the y-intercept for this one, I have to substitute in 0 for x. So 0 is going to go in for the x value right here. So f of x is equal to 350 minus 14 times 0. Well, 14 times 0 is just 0, so I'm left with 350, which means y is equal to 350. That's not the coordinate point. Remember, I have to write it that way. So 0 through 50 is my coordinate point. Now, I didn't graph this one, and maybe we should have. But again, the graph, the scale would be wildly off here. If we got to go all the way up to 350, at 0, 350, let's say that that's the top of the scale. 25, 0 would be like this, somewhere in here. Okay, so your line would look something like that. All right, last one, and then we're done. Kim. She owes her friend $245 and plans to pay $35 per week. Write an equation of the function that shows the amount that Kim owes after X weeks. Then find and interpret the intercepts of the function. So that's our function. F of X is equal to 245, and I'm subtracting $35 every week. That's what X represents. So again, if I'm finding the X-intercept, 0 goes in for the other, 0 goes in for Y. So you're seeing, I'm going to extend this page a whole bunch of times. Stop doing that. So you see me substituting in 0 for f of X. As I solve for X now, so 9 is 245 from both sides. I get negative 245 is equal to negative 35X. Divide both sides by negative 35, and I get 7 is equal to X. Again, that's not the coordinate point, but 7 comma 0 is. And again, just to want to reiterate, that 0 right here that went in for Y is the reason why we have a 0 there. Okay, so I have the coordinate point 7 comma 0 for that particular line. When I graph it, I want to find a y-intercept. Remember, 0 goes in for the other, so 0 is going in for X here. So f of X is equal to 245 minus 35 times 0, 0 in for X. 35 times 0 is just 0, so I get 245, so that means Y is equal to 245. That's not a coordinate point, so I have to have the coordinate point 0, 245. So I also had to interpret each of these. So remember, it's a scenario of borrowing money, right? So what does 7 comma 0 mean? Well, 7 represents weeks. What that means is that the balance, Y, will be 0 after 7 weeks has gone by. Same scenario happens if we have 0, 245. What that means is that if we have 0 in for weeks, it says no, it means no time has passed, and the balance is still $245. And again, if we wanted to graph this, I can sketch this briefly. Okay, 7 comma 0. If we got to go all the way up to 245, 0, 245, let's say is like way up here. 7 comma 0 would be like here, right? And then we have our 2 points on the graph, and we can graph them. All right, ladies and gentlemen, that is your video lesson. I hope you found it helpful. I hope you guys are doing great, and we'll see you again in the next one. Peace.